All right, so now we're going to talk about the last aspect of the signals in NMR, multiplicity. Now, multiplicity, at the outset, it's a relatively simple concept. It's simply a splitting pattern of the signals, okay? So you're going to get some signals that look like this, and that's called a singlet. You're going to get some signals that look like that, and it's called a doublet, a triplet, a quartet, and so on. Now, this is one signal. It's one group of hydrogens, but it's been split. All right, and it's called multiplicity. It's the splitting pattern. What splits it? This is relatively simple. The thing that splits it is its neighbors. All right, multiplicity results from the magnetic effects that protons have on each other. So if I want to measure the magnetic field around HA, right, there's first of all the external magnetic field, right, but then there's also the magnetic field that's put off by this guy here, his neighbor, right, and you see his neighbor is on the carbon, which is next to the carbon on which the HA is. All right, so you can see what the neighbors are, but you're going to be tempted sometimes to see another hydrogen which is close by. It's not technically the neighbor because it's not close enough. So we got to get used to this, right? It's 1, 2, 3, 4. 1, 2, 3, 4. There's the neighbor right there. There's one neighbor. So the magnetic field that the proton HA feels is a combination of the external magnetic field and the magnetic field of the B proton. Now, if the B proton is against the field, the sum of these two fields, against the external field, okay? Then the sum of these two fields feels different than the sum of these two fields, where the external field is aligned with the field of HB, okay? So really, in essence, if there's one neighbor, if n is equal to 1, then n plus 1 is equal to 2, and we're going to get a doublet. All right? A doublet means that there must be, let's see, n plus 1 is equal to 2. There's the doublet. The number of neighbors must be 1. That's how we're going to do this every time. We're going to look at it. We're going to say n plus 1 is blank, whatever that is. And we're going to go, oh, the number of neighbors must be n. And that's always going to be the case. All right? All right, so let's look at another example. Suppose that we want to measure HA, but now HA's got two neighbors. Okay, now don't be fooled that this HB is down here. You remember, right, Lewis dot structures are not necessarily the three-dimensional shapes. Both of these protons are equally close to this HA. All right, so that means that this guy has got two neighbors now. N is equal to 2. N plus 1 is equal to 3. It's going to get a triplet. Boom. Right? Why? Well, because the external field either matches up with both protons being against it, or one of each being with it, or against it, whatever, you know what I mean. And it also sums with both of them being with the magnetic field. So either way, if you have two neighbors, n plus 1 is 3, you're going to get a triplet. Now, what if you have three neighbors? You already know where I'm going with this, right? I saw when I brought this picture in, it didn't have HB here. So if I have three neighbors, look at, I want to measure the magnetic field on HA. How many neighbors does HA have? It has 3, right? Watch, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So all three of these hydrogens are his neighbor. Well, if n is equal to 3, n plus 1 is equal to 4, and so it's going to be split up into a quartet or quadruplet. All right. Now, table 15.3 shows how the multiplicity trend continues. All right, it's just the same thing. You would guess it's n plus 1. By analyzing the splitting pattern of a signal in proton NMR, you can determine the number of equivalent protons on adjacent carbons. All right, we've seen this before. I've already said this. Where n is the number of neighboring protons, n plus 1 peaks is the signal. So we can look at the signal and know that that signal multiplicity is n plus 1, right? So we take 1 away from that, and that is the number of neighbors. Where am I here? Remember now, 3 key things for splitting, okay? This is critical. Equivalent protons cannot split one another because they resonate together. So if you've got, for example, ethane, right? These are all equivalent, so they they're sort of neighbors, right? 1, 2, 3, 4, right? Can you see that? 1, 2, 3, 4. They're neighbors, but they're equivalent, so they cannot split each other. So you do not get any splitting with ethane. Okay? To split each other, protons must be within a 2 or 3 bond distance, and really, two bonds. It's the neighbors. This is too far. You can see this. That's too far apart. Not going to split. This does split. Okay, and occasionally this will split if these are non-equivalent protons. But mostly the splitting we see are going to be on the neighboring carbons. Okay, so the first rule is equivalent protons don't split. The next one is they've got to be within 2 or 3 bonds in order to split. If it's 4 bonds away, it's not going to split anymore. And finally, the N+1 rule only applies to protons that are all equivalent. Okay? So if you've got HA, HB, and HC, because let's say those are different, right? Suppose these are different. Then even though HA's got, let's see, 3 neighbors over here and 1 more over here, they don't split the same way because the neighbors are not equivalent. All right, that's going to come up, I say here, that's going to come up with some complex splitting we'll discuss later in this section. We actually might just skip it because it's super complex. We're mostly going to be interested in being able to appreciate simple systems for now. All right. Now, the degree to which a neighboring proton will couple to its neighbor, it's called a coupling constant, or its J value. The J value is the distance between peaks of a splitting pattern measured in the units of Hertz. Okay, so you can see if JA and JB, the coupling constant is going to dictate how far apart they go. Okay, we're not even going to be using that for calculating. All right. Higher field strengths will give better resolution between peaks. So if you have a 300 megahertz spectrometer, it's going to give better resolution than a 60 megahertz spectrometer, right? These would be like the same peaks, but you can see you get better resolution if you get essentially a more expensive apparatus, of course. Okay. So, and it's also important, I think, to watch out for recognizable patterns. So earlier in a previous conversation I was having with you, I saw a 4 and a 3, and I immediately knew it was an ethyl group because it was a 4 and a 3. So look at this. If you've got this right here, he has 3 neighbors, right? 3, and n is equal to 3. And so n plus 1 is equal to 4. So this guy's going to get split into a quartet, right? This one has got 2 neighbors, right? You can see the 2 neighbors are the blue ones over here, right? N is equal to 2. So n plus 1 is equal to 3. These 3 are going to get split into a triplet, right? You've got to watch out. These 3 H's do not correspond to this triplet because, look, 2 goes to a quartet, right? The splitting has to do with the neighbors. Big deal. So if you get an isolated ethyl group, you're going to see this is an ethyl group right here, right? If you get an isolated ethyl group, you're going to see this pattern. It's very common. This will be close to 1, and this will be slightly upfield at maybe 1.5 or 1.7. Okay, and it's super helpful. When you see that, you immediately know you've got an isolated ethyl group. Okay, now, you know what? I think we're going to stop there. I think that's all we need to say about multiplicity. Okay, I do want to add one slide here to this last conversation about multiplicity. It turns out the splitting is not always observed, all right? So, for example, with ethanol, right, you've got this proton here, and you go, well, look, its neighbor then, watch, 1, 2, 3. There's a neighbor, and there's a neighbor. So this guy should have 2 neighbors, right? N is equal to 2. Well, it turns out that oftentimes with ethanol, we don't see splitting at all. And that's because, well, I'll show you in the next slide. But I think the important point is alcohols oftentimes don't have splitting. The protons bonded to carbon, they split each other, but the hydroxyl proton is not split in alcohols oftentimes, and here's the reason why. The reason why is because you have trace amounts of acid in solution. I mean, it could be very small amounts of acid in solution. But if you have a very small amount of acid in solution, then this ethanol can act like a base, boom, boom, right? And then water will come back and act like a base and take away this proton. So look, we started out with this hydrogen here, and we ended up with this one in the end, right? So it's really called proton exchange. Proton, how do you spell exchange? E-X, change, okay? Proton exchange means that the relationship this hydrogen has with that oxygen is transient, all right? And such exchange blurs the shielding and deshielding effect of the neighboring protons, and it gives oftentimes a singlet, and it also broadens it. And I think that's all we want to cover with respect to multiplicity.